Obviously, we've been talking about acid and bases, and we've seen a number of different ways to figure out if a solution is acidic or basic or neutral. We had our Kw, which is our H plus concentration, times our OH minus concentration equals 1 times 10 to the minus 14. Here you can calculate either the H plus concentration or the OH minus concentration, depending on which one is given to you. You could compare the two and decide if it's acidic or basic. If the H plus is greater than the OH minus concentration, which again means basically your acid part is greater than your base part, it will be acidic. If they do equal each other, they will both have the same concentration of 1 times 10 to the minus 7, and that would give you a neutral solution. If the H plus is less than the OH minus, or the OH minus is bigger, that means the basic part of the solution is greater than the acidic part, and it will give you a basic solution. We talk about the pH scale, which again runs from 0 to 7 to 14. Less than 7, acidic. Greater than 7, basic. And at 7 on the nose there is neutral. 7 going towards 0 means it's becoming more acidic. And 7 heading towards 14 means it's becoming more basic as you go in that direction. You could calculate the pH by using the pH equation there, which is the pH is equal to negative log of the H plus concentration. It does tell you actually in the name, again, what you need to calculate it. pH means you do need the H plus concentration. Remember, as we've also talked about a number of times, H plus and H3O plus, basically the same thing. So could replace any of the H pluses there with H3O plus, and it is the same thing. We also talked about a scale that's similar to pH, but it actually measures the OH minus concentration, and that is what is known as the POH scale. And the POH is negative log of the OH minus. So once again, it kind of tells you here you need the OH minus for that. And the reason why you might want to calculate the POH is if you're given the OH minus concentration, there's a nice relationship between pH and POH, which is if you add them together, they do equal 14. And that means, again, if you have the OH minus given to you, you can calculate the POH, subtract 14, and get the pH from that, again, without having to do some other things. Um, Remember, though, asked, is the solution acidic, basic, or neutral? There is just one answer, as we've been talking about, to that question. You should probably always look at the pH value because that's the scale most people have in their head, and that's the one that you definitely want to look at. Thank you. Again, don't fall into the trap a lot of people do where they calculate the POH and the pH, and then they kind of give both answers like it's acidic and basic. So the POH scale, as we talked about last time, runs opposite of the pH scale. So if you have a high pH, you will have a low POH, and vice versa. If you have a low pH, you will have a higher POH. But that scale is mostly what most people have. We also talked about that if you have the pH, you can get directly from that the H plus concentration. So if you're given the pH, you can calculate the H plus concentration, and that is equal to the inverse log of the negative pH. And again, usually on most people's calculators, when they punch that, a 10 and a caret pops up when they do the inverse log, and you want to make sure it's negative in that case. To get to the inverse log, usually you have to hit the second or shift button, top left corner of your calculator, and the log button to do that. We could also do that for the POH. So if you have the POH given to you, you can directly from that get the OH minus concentration. It's the exact same calculation, the inverse log of the negative POH. Remember that depending on if you have a display calculator or a non-display calculator as to how you need to punch these in. So again, if you have a display calculator, pretty much you're just going to punch it into your calculator exactly the way it's written, sort of in that direction. If you have a non-display calculator, then you usually have to go backwards, which usually means you have to start with the number and then kind of do the other parts of it to get it to punch in correctly. Any questions on any of that stuff there? Okay. All right, so why don't we try this one here? We have a pH of 5.67. What is the pOH of the solution? Why don't we also figure out the H plus concentration, the OH minus concentration, and is it acidic, basic, or neutral? So take a few moments, make sure your calculator works. Okay, let's take a look. So again, we have the pH, which means we have really two options. We could go directly and get the H plus, or we could directly get the pOH. I'm going to do the pOH first, and that would be the pH plus the pOH is equal to 14. So in this case, the pOH here would be 14 minus our pH of 5.67. And that's going to get us here, looks like 8.33 in this case. Now that we have both the pH and the pOH, we could actually get the concentrations from it. So again, we're going to do the H plus concentration, which would equal the inverse log of the negative pH. And again, on your calculator, that's going to look something like this when you punch it in. And once again, depending on your calculator, second or shift, log, negative, and 5.67 and equals if you have a display calculator. Again, a non-display calculator, you could go 5.67, then hit the negative button, then hit the second button, and then hit the log button. So any one of those ways should do that for you. And if you do that here, you will end up with too many zeros to count. Let's go scientific notation. You'll end up with, it looks like 2.1 times 10 to the minus 6, and we do need molarity there for our concentration. Once again, something that we talked about last time as well in terms of significant figures. Because this has two decimal places, we end up with two significant figures here when we go backwards. Obviously, it's the opposite as you calculate the pH to significant figures to decimal places. We can, at this point, actually have two options. We could also use KW at this point to get the OH minus, or we could do our kind of OH minus from the POH as well. Over here, actually, we could do that. So I'll do the same thing with the OH minus. It will be first log of the negative POH, which will again give you a 10 and a caret, negative 8.33. And if we do that there, and again, you can use, like I said, K at this point. Fine. Lastly, here, we always want to look at the pH in terms of acidic, basic, or neutral if we have it. And that obviously is less than 7, which means it is an acidic solution. Any questions on any of those there? All right, so let's take a look at a couple more here, maybe. All right, so why don't you we'll just do what it asks in this question. The pH of the solution is 3.14. Okay, so again, in this one, we have the pH and we want the H plus concentration, so we can get that directly from it. Just the same calculation we just did there, the inverse log of the negative pH. Again, punching that in correctly will look something like this, probably on your display if you have a display. And if we do that there, we're going to do a little inverse log action here, negative 3.14. It's going to give us a 7.2 times 10 to the minus 4 molar. Again, two decimal places here, two significant figures is what our concentration should end up being. Um, Again, your calculator may not give it to you in scientific notation. Obviously, it may be in decimal form as well. This obviously is also still an acidic solution as the pH is less than 7. Any questions on that calculation there? All right, one more here. What is the OH minus concentration here if the pOH is 5.67? Okay, so in this case, we do have the POH, and once again, it does tell you kind of in the name what you could get from it. So you can directly get the OH minus concentration from a POH, and it is the same calculation, the inverse log of the negative POH. And again, that's going to get you something that looks like so here. And punching that in here, going to get us a 2.1 times 10 to the minus 6 molar. Once again, two decimal places, two significant figures as we go backwards here. Question on that calculation there. Now, this solution is actually basic. And I know that from if I did calculate the pH plus the POH is equal to 14. The pH is equal to 14 minus our 5.67. And that gives us a pH of 8.33, which is basic. So remember, pH is what you want to look at, not POH. They run opposite of each other. So just make sure you keep that in mind. Very common error that people make a mistake on sometimes. Any questions on that there? All right, the next thing we're going to talk about is what happens if you maybe have an actual formula given to you. So if you have the pH of a strong acid or really even a strong base. So most of the problems up to this point have been more kind of like generic sort of concentrations, like the H plus concentration or the OH minus concentration. But you may also be given an actual formula for an acid or base, and how do you calculate it if it is a strong acid or really even a strong base? Well, first off, we should review again what are strong acids. So there is sort of a list of kind of six or so there are strong acids. And again, it's a good list to know. That is hydrochloric acid, nitric acid, perchloric acid, sulfuric acid, hydrobromic acid, and hydriodic acid. So this list of kind of six strong acids are important uh, for this chapter for sure, and later on in your chemistry career if you go to 1B as well. It's a really good list to know because you could generally make a pretty good assumption that if it is not one of these six, then it probably is a weak acid, which would require a different type of calculation. So just by process of elimination, you could also know perhaps if you're dealing with something that is a weak acid, if it's not one of those there. Strong bases, on the other hand, typically have hydroxide in them. So a lot of strong bases have hydroxide like sodium hydroxide, potassium hydroxide, calcium hydroxide, and so forth. Basically, if you go to the periodic table and you start at where lithium is and sodium and potassium and hang a right-hand turn to calcium and then kind of down the strontium, right out of room there, we'll go barium as well. If you hook up anybody in group 1 on a periodic table or group 2, these guys here, and they have hydroxide in the actual formula, they're most likely going to be a strong base. So most of our strong bases come from group 1 and group 2 on the periodic table that have actually hydroxide in them, and that makes them a strong base. Now, what is a strong acid or strong base has to do with the pH? Well, they are strong acids and strong bases because they really are strong electrolytes. And if you remember, strong electrolytes 100% break apart into ions in solution. So they 100% break apart into ions in solution. And that's important. For example, if we did take something like our HCl here, in solution, it is not going to stay together. It's going to completely break apart into an H plus ion and a chloride ion. And this is what you're going to have 100% in the solution. So if you had like a beaker of hydrochloric acid, that's pretty much what you got going on. You have basically just these ions floating around. There is none of these sort of units still together in the solution. They've all completely basically broken apart. Now, what's important about that is if you think about the pH is equal to negative log of the H plus concentration, which means that is the most important thing to figure out what is the concentration of it so you can calculate the pH of the solution. This is where we talked about molarity and concentration of ions comes into play. The good news here is if you know the molarity of this guy, the whole thing, it is a 1-to-1 relationship between those two things, and it would be the exact same molarity for the H plus concentration. So the good news about most of these strong acids is they are monoprotic, which means they will only give away one H plus. So if you know the actual concentration of the acid, the whole thing together, that will usually be the exact same number for the concentration of the H plus, which is what you would need to calculate the pH. So, for example, if we had a zero point 0.1 molar hydrochloric acid solution, we would do the same thing. We would have our hydrochloric acid, which is a strong acid. It would break apart into, again, H plus and Cl minus. And because the concentration of this guy is zero point 0.1 molar, it's a 1-to-1 relationship here, which means the concentration of the H plus will also be 1 molar or zero point 0.1 molar. It is also, for curiosity's sake, here 1-to-1 between the chloride, which is not important in this calculation. It would also be 0.1 molar as well. So since that is the concentration of the H plus, we can go into our pH, which would be negative log of 0.1 molar. And for this hydrochloric acid solution, that will get us here a pH of 1 in this case, which definitely is acidic. So the good news is if it's a strong acid, pretty much you have the H plus concentration, you go right into it. How does a strong base work? Well, if you had something like sodium hydroxide, and let's just say we had the same deal, zero point 0.1 molar sodium hydroxide, because that is a strong base, it also will 100% break apart into sodium ions and hydroxide ions. Now, in this case, you will have 100% sodium ions floating around and hydroxide ions. Now, in terms of the pH, there's obviously no H plus there. That's important. But here, what's important is actually the hydroxide. That will allow us to calculate not the pH, but we could calculate the pOH. And once we have the pOH, we could subtract 14 and get the pH from it. So it works kind of the same way. It's a 1-to-1 relationship here between the sodium hydroxide and the OH minus, which means the concentration of the OH minus would also be 0.1 molar. We could put that into here again, the pOH, because that is the OH minus concentration. And that will be negative log of the OH minus. And that will give you negative log of 0.1, which will give us a 1. Once again, that is not the pH, but that is the pOH. We can now get our pH by taking 14 minus our pOH, which is 1. And that now gives us a pH that makes more sense because that is a pH of 13, which is basic. And obviously, sodium hydroxide is a strong base. So we would expect it to be a basic pH. So if you have a strong acid or a strong base, you're basically just trying to figure out the H plus concentration for your strong acid, which means in most cases it's going to be the same as the actual whole thing. For the strong bases, you're really figuring out what is the correct concentration of your hydroxide. You could calculate the pOH and then you could get into the pH. Any questions on that there? Okay. So why don't you try these two here, both a strong acid and a strong base. What is the pH of each of them? Okay, let's take a look. So once again, this is on that list of strong acids. So you definitely know it's a strong acid. And that means that it is going to completely break apart. And again, it will basically lose a H plus here or give away or break into an H plus, and we'll make some perchlorate here. And once again, it is in this case the H plus that is important for the pH for us to calculate. And once again, because this is a 1-to-1 relationship, we do know the concentration here of the whole thing. This would then be 1 times our 0.05 molar, and that would give us 0.025 molar as our H plus concentration. And that is what could go into our pH, 0.025 in that case. And that's going to get us here minus log of 0.025. Looks like a 1.60, which definitely is acidic and would make sense as this is a strong acid. Any questions on that there? Now, for our purposes here, you could probably safely assume in most cases that if you're given a formula, it's a strong acid. Weak acids to calculate the pH is a much longer calculation and something you'll learn in 1B. So at least for our purposes, you can probably assume if you're given a formula of an acid or a base, it probably is going to be, in this context here, calculating the pH, a strong acid or strong base. With that being said, that is one of those strong bases. Again, group 2 with hydroxide there to the right of potassium. That means that this is going to break apart 100% in solution. So here it will break apart into a calcium ion. And the important part of this is it will actually give you not one, but it will give you two hydroxides here as that breaks apart. And that actually is kind of important in this calculation. We do want to figure out our hydroxide so that we could get to our pOH. When we have our 0.025 molar, it is now a 1-to-2 relationship, not a 1-to-1 relationship here. So we do need to multiply our concentration by 2 to get the hydroxide concentration. So the proper hydroxide concentration in this, because it's not a 1-to-1, actually is 0.025 times 2, gives us 0.05 molar is our hydroxide concentration. Now that we have that, we could use it to calculate our pOH minus the log of our hydroxide. And that is going to yield us a 1.30. Now, in case you got confused or something and you thought that this was the pH, it really shouldn't make sense to you because that's a base and that would then be an acidic pH and that wouldn't really make sense. So this is the pOH. We want to calculate our pH would be 14 minus the pOH. So that's going to be 14 minus 1.30. And that's going to get us here a pH that makes a little bit more sense at 12.70. That definitely is basic and would be the pH in this case. I would say probably with the bases, the strong bases, the ones that come from group 2 are probably the only ones you have to worry about that, kind of has to adjust the concentration of hydroxide. You really don't have to worry too much about that with the acids, as I mentioned, because most of them that are strong acids have only one H plus, which means basically it's going to be a 1-to-1 relationship. Any questions on how to calculate from a strong acid or a strong base? All right, the last thing we're going to talk about in this chapter are buffers and buffered solutions. And a buffer solution is a solution that has the ability to resist changes in a pH when you add more acid or base to it. So very often people have a wrong idea about what a buffer solution is. They oftentimes think a buffer solution is a neutral solution, and it can be neutral, but you could also have a buffer solution that's acidic. You could also have a buffer solution that is basic. You could actually create a buffer at any pH along the scale you choose. So you could actually have a buffer solution that has any pH you like, acidic, basic, or neutral. What a buffer is able to do is whatever pH it starts at, if you add some acid to it or you add some base to it, it will be able to maintain that pH. You will not see a really big jump in the pH or drop in the pH when you add acid or base. So if you had a buffer at like a pH of 5 and you added some acid to it, it will still stay around a pH of 5. It may go down just a little bit, maybe 4.9 something, but it'll stay in that 5-ish range. It will not go from like 5 all the way down to like a pH of 1, a really big drop in the pH when you add acid. Same idea if you were add base to that buffer, if it's made properly, it will go up maybe a little bit, but not a big jump. So maybe if you add some base, it goes from 5 to like 5.1 or something like that. It will not go from like 5 to like a pH of 12. So you won't see these really big changes in pH. The reason a buffer is able to resist changes in pH is actually what it is made out of. And a buffer is made out of two things. It is made out of a weak acid and its conjugate base, or you can make a buffer out of a weak base and its conjugate acid. Now, what is that sort of relationship there? That is the Bronsted-Lowry definition. The only difference between the weak acid and its conjugate base, so the only difference between these guys is really an H plus, and the only difference between these guys is an H plus, is that Bronsted-Lowry definition. They do have to be weak. You cannot have a buffer made out of a strong acid or a strong base. So if you ever come across a question where it's like, hey, can these things be a buffer? The first thing you want to do is identify what type of acid or base is there. And if it is weak, then you're probably good. If it is strong, then it cannot be a buffer. So the list of 6 strong acids we just talked about is important, and also those strong bases, because if you're trying to make a buffer out of something that's on that list, you cannot do it. So you cannot make a buffer out of any of those things that are strong. Also, those lists are good for the process of elimination. If it's like an acid or base that's not on that list, then you probably have a good shot at making a buffer out of it because it's probably weak. And the reason why it's able to do that is a weak acid or a weak base is a weak electrolyte. And if you remember, a weak electrolyte will mainly stay together, but break apart a little bit. So, for example, if you took acetic acid, which is a weak acid, and by the way, I know acetic acid is a weak acid because it's not one of the 6 on my list of strong acids, so it's definitely going to be a weak acid. When it's in solution, it will break apart a little bit into H plus and acetate here. And this is acetate. And this is a weak acid. And this right here is his conjugate base. So that is your buffer solution right there. These two things are going to act as a buffer. And again, the difference between those two things is just one H plus, and that is what's going to act as a buffer. Why is that important? If you remember that we have these arrows that head in both directions, that is a reversible reaction, and that sets up an equilibrium. So when we have something that is weak, it will set up an equilibrium. And what that means is the rate of the forward direction will equal the rate of the reverse direction. And what that actually allows you to do in a solution is, if we were to look at this in the beaker, we put some acetic acid and some acetate in it, or sodium acetate. We can have this equilibrium set up where we will have our acetic acid, arrows and all in the beaker, H plus, and acetate. And Both of these things will actually be able to remain in the solution because it sets up this equilibrium. So you basically have in the solution floating around an acid part of the buffer, and you also have a base part to the buffer. Now you increase the amount of, say, acetate in here because you will add something referred to as like sodium acetate, and that is sometimes referred to as the salt of its conjugate base or the salt of its conjugate acid. And while you add some of that sodium acetate, that's a source of acetate, which kind of makes that concentration get bigger. And we also have obviously our acetic acid in there. And that's really important. And that's really what allows a buffer to work is the presence of both of those things. So a buffer has an acid part to it and it has a base part to it. And because they come from a weak acid or a weak base, they're able to keep both of those things in the solution at the same time. And that's really important for how it's able to function. Why can a strong acid or strong base not be used as a buffer? So if you wanted to make a solution out of HCl and say sodium chloride, and sodium chloride is basically chloride. So this would be what you would try to do for your buffer, which is a strong acid like HCl and its conjugate base. So this is our acid, strong acid, and that would be its conjugate base, which comes from sodium chloride. Now, the problem with that is when you put those into the solution together, because HCl is a strong acid, it will not stay together. It will break apart, and you will basically get H plus and Cl minus floating around in that solution. The sodium chloride will break apart into sodium and chloride. And now what you have in this solution is really only the base part. You don't have any of the acid part in that solution, and that's not going to allow it to be a buffer, and that's why it cannot work as a buffer, and that's why this will not work as a buffer because you only have one part of the needed part for a buffer to work. Same thing would happen if you try to put like sodium hydroxide and use that as a buffer. It will not work either because it's not going to stay together. So because a weak acid or a weak base is a weak electrolyte, it actually is able to stay together in solution and have both an acid part and a base part in that solution, which is really important for how it functions. Any questions on that there? So, when we talk about buffers, very common buffers are things like acetic acid, like you're going to use today, I think, in lab, and sodium acetate. This is again a weak acid, and this is the salt of its conjugate base. It is referred to as the salt of its conjugate base because it has a sodium ion there to balance it out. A salt is an ionic compound. What the sodium acetate is really sodium ions and acetate ions. And the sodium here is really not doing anything other than just floating around, having a good time. The actual buffer component here is the acetic acid and the acetate. That's the actual buffer part of the solution is these two guys together. Again, it's referred to as the salt because it'll usually have some type of spectator ion like a sodium, a potassium, something like that, just floating around. You could do something like HF, for example, is a weak acid. It's not on that list. And something like sodium fluoride, which is a salt of its conjugate base, a weak acid, and the salt of its conjugate base. Again, because this is a solid ionic compound, it's a strong electrolyte. It will break apart into a sodium ion that's not important for the buffer, but it will make this fluoride. And again, this is basically your buffer here, these two guys that are reacting to weak acid and really is conjugate base. Something like bicarbonate and carbonate buffer, like in the blood, is a buffer that is used a lot. And again, the difference here is an H plus, and that is a buffer. Sometimes it is written as, say, sodium hydrogen carbonate and sodium carbonate. Again, here it is this part and this part that's the buffer. The sodium is really not doing much. It's just there to balance out the charge. This again is really your buffer component. So you could also have a weak base. Ammonia is probably the most common weak base you could come across. And you could have ammonia, something like ammonium chloride as a buffer, and that is a weak acid and its conjugate base, conjugate acid. There we go. And it's really the salt of its conjugate acid. Once again, ammonium chloride is a salt that will break apart into NH4 plus and Cl minus in solution. And it is this ammonia and the ammonium that is really the conjugate acid, and that is really your buffer here. So these are some examples of some buffers. What they all share in common is they have either a weak acid or a weak base, and they have their conjugate partner. Again, sometimes, a lot of times, they'll be written with that salt, like a sodium, potassium, something like that. In this case, a chloride is just hanging out, not really doing much in that solution. But those are really the makings of a buffer. Any questions on that there? Now, how does a buffer work and how does a non-buffer work? So let's take a look at example here, which is water. And water is not a buffer. So if I took a strong acid and added it to water, if I took something like hydrochloric acid and I added that to water here, my H2O, and I took some HCl and I dumped it in. What would happen in this particular case is, because hydrochloric acid is a strong acid, when it goes into my water, which is not a buffer, it is going to completely break apart into H plus and Cl minus. And it's going to 100% break apart into these ions. So what happens in this case is, when you dump that in, you create a lot of H pluses really quickly. Some chlorides as well, not important. But you create a lot of H pluses really quickly in that solution. So what happens in that solution is the concentration of H plus skyrockets, basically, because you added a bunch of acid in there. And as we know, when the H plus concentration goes up, the OH minus concentration goes down, and the pH goes way down. So if we were to take the pH of our water, maybe we'll just say it was 7 to begin with, and you added the HCl to the water, the pH may go from a pH of 7 all the way down to like a pH of 2 or 1, depending on what you added. And you'll see a really, really big jump in pH because you created a lot of free H pluses. And that affects the pH because obviously the pH is calculated based on the concentration of H plus. So by increasing the amount of H plus in that solution, you will see a big jump in pH. And that's why water is not a buffer, because it cannot handle all that H plus that's coming in, and it allows it to basically be formed. Now, if I took some sodium hydroxide, which is a strong base, that's our strong acid. This is our strong base. And I add it to, again, a beaker of water. Because it is a strong base, just like the strong acid, it's going to 100% break apart into ions. It'll break apart into a sodium ion and some hydroxide ion. And again, 100%. So when you do that in our beaker of water, we now have a lot of sodium ions, which is not super important. But more important is we have a lot of hydroxide ions that have now been formed, a lot of these free hydroxide ions. And what that means is the concentration of OH minus increases, the concentration of H plus will then decrease, and we will actually see the pH go up because now we have a smaller amount of H plus, and that will give us a higher pH value in this case. And again, here, if our water started at like a pH of 7, After you add the base to it, maybe it jumps to a pH of 10, 11, 12, something like that. A really big jump in pH because you just introduced a lot of free OH minus to that solution. And remember, those are the two things that could really affect the pH of a solution is how much free H plus is in there or OH minus is in that solution. First off, any questions on how a non-buffer to hand do it here? So now let's take a look at what would happen if we added these exact same things to an actual buffer. And I'm going to use the hydrofluoric acid because I don't feel like writing acetic acid and some sodium fluoride as my example. So this is my buffer. And again, that is a weak acid and his conjugate base or the salt of his conjugate base. Once again, the actual buffering parts is the HF and the F minus from here. And that is the actual buffer parts of our solution. So if I have this as my buffer in solution, because that is a weak acid, it is not going to 100% break apart. It is instead going to set up this equilibrium of HF, we'll include the arrows, H plus and F minus. Now, once again, as we talked about before, what we now have in this solution is the acid part of the buffer, and we have the base part of the buffer. And this again is our buffer, right? Now, the base part of the buffer is mainly coming from this guy. That's going to supply a lot of F minus in that solution. And obviously here our HF is going to supply obviously the HF. And both of those things are in the solution floating around. So now what I want to do is I want to add to this buffer. I want to now add some HCl, which is again a strong acid. So I'm going to go and dump my HCl in here. As we just talked about, HCl is basically a source of those two things. H plus and Cl minus is going to go into the solution. So when I do this and I put my hydrochloric acid, which obviously is an acid, when it reacts with the buffer, should it react with the acid part of the buffer or the base part of the buffer? It should react with the base part of the buffer, right? Because they're called acid-base reactions. So when I add HCl into my buffer, it's going to actually go find the base part of the buffer. And that's my base part of my buffer. And it's going to do a double displacement reaction, as that is a positive negative. That's a positive negative. They're going to switch partners. So we're going to get this and this come together. And now what we're going to get is HF being formed, and sodium chloride is going to be formed in this case when they basically switch places. Now, a couple of things that are formed. This always happens in a buffer situation. We actually formed part of the buffer. So we actually made some more HF as a result of this reaction. And that always happens. So since HF was part of the buffer originally, that's definitely not going to screw up the pH. We also made this guy here, which is a salt. And this is a neutral salt, which means it will not mess up the pH either. But it is actually what we don't see here that we did see when we added the HCl to water. That's really the main difference. And if we come back here, when we added the HCl to water, what we actually saw was we made a lot of free H plus was formed. So a lot of free H plus was formed. Over here, there is no free H plus formed. That H plus got tied up when it went in for a swim with the fluoride and basically made HF. So the result of that is we didn't make any more H plus. So the amount of H plus that was in that solution to begin with stays relatively constant. So the amount of H plus stays relatively constant. And because it stays relatively constant, the pH will also stay relatively constant. And what I mean by relatively constant is if you were following this with like a pH meter, you would see the pH change. It would go down just a little bit, but it would not have a giant drop in pH like we would see in water. And that's because we're not making a lot of free H plus. So what happens when this goes for a swim is this H plus ion goes and finds the fluoride, and then it makes some HF. And the result of that is we don't get any of that free H plus in the solution. It keeps the H plus concentration relatively maintained, and we see just a mild drop in the pH, not a gigantic swing in pH because of that. Any questions on that there? Now, what would happen if we did this with our base? And we'll use the same buffer here. So we're going to take our buffer. And again, this is our weak acid and our conjugate base. And again, we will have our beaker here where it will set up that equilibrium in solution. And again, we will then have, just like before, our acid part floating around in there and our base part. But now in the case, we want to add actually a strong base to this. And if we were going to add a strong base like sodium hydroxide, and we want to drop that in, that again is a sodium ion and a hydroxide ion that's going to go for a swim. When I add some sodium hydroxide, which is a strong base, it is going to react with the acid part of the solution to give us our acid base reaction. So we'll get this reaction that's actually happening. This also is a double displacement reaction where we're going to switch partners. And that's an acid base, which means we are going to make water and a salt, which in this case is NaF here. And once again, here we do make water, which obviously is not going to mess up the pH. And just like before, we actually made part of the buffer. So we made some part of the buffer. And that also is not going to mess up the pH. It is, again, much like with the acid, what we don't see, like what we saw when we added the strong base to the water. When we added a strong base to the water, we made a lot of free OH minus into that solution. And as a result of this, we did not make a lot of free OH minus. And that means that the OH minus concentration stays relatively constant. And because the H plus concentration is tied to that, it will also be relatively constant. And that's going to keep our pH also relatively constant. Again, the amount of H plus that was originally in that solution is going to stay relatively the same. Will you see a change in the pH like we talked about? You will go up a little bit, but we won't see a really big jump upwards in the pH like we would see in water. So in this case, what's happening is the hydroxide here is actually going in here and making water. And the result of that is we're not making that free OH minus in that solution, keeping everybody relatively constant. So this is how a buffer is able to resist big changes in pH, is because they have both an acid part and a base part of it. And when you add additional acid or additional base to a buffer, it prevents the formation of free H plus in the solution when you add acid. It prevents the formation of free OH minus in solution when you add base. Both of those would have a big effect on the pH. And because it doesn't produce a lot of those things, the pH stays relatively constant. You don't get these big jumps in pH or drops in pH. They go up and down just slightly, but no real big drop. So picture-wise, if you kind of look at a buffer, typically you would want to make a buffer that has an acid part and a base part that's about the same amount. And that is when you add more acid to it, it will react with the base. But as we saw, it will actually make dramatically drawn here, more of the acid part of the buffer as a result of that reaction, and you'll use up a little bit of the base part of the buffer. And same thing if you add base to it, a buffer, it will react with the acid part, but you'll make more of the base part of the buffer, and you'll use up some of the acid part of the buffer. And it is sort of self-generating in a sense. You use a little bit part of the buffer, but it'll make the other part of the buffer. There is what is known as buffer capacity, which means you can blow through a buffer. What would happen if I continuously didn't read instructions, grabbed too strong of an acid, or kept adding acid? Every time I add acid, I am just going to start chewing up the base part. So every time I add acid, I'll chew up the base part, chew up the base part. And at some point, it is possible for you to blow right through the base part of your buffer. By the way, that is what happens when you did your titrations the other week, when you had just added one drop and it went like super pink because the pH jumped a lot. You actually made a buffer and then you actually blew through it because you kept adding sodium hydroxide to it and you blew through that part of the buffer. At this point, if you continuously added acid, you're just going to add H plus in and you'll see a pretty big jump in the pH. So it is possible to blow through a buffer. There is a buffer capacity. When you actually make a buffer, you want to make sure that it is appropriate in terms of the molarity to handle whatever acid and base you're adding to it. If you add too strong of an acid for a buffer, it is possible just to blow right through it. It won't be able to resist the change. But if you make a buffer that is correct, and here's a table from your book that describes the buffers, if you make it correctly in terms of its concentration based on what you're adding, it should be able to resist big changes in pH over a long period of time. Any questions on buffers there? All right, that wraps up chapter 16.